Today I'll be sharing the sounds of silence, lessons from an 18-hour API outage. I'd like to start by talking about bugs. Bugs are a constant companion of an engineer. Anytime a change is introduced into a complex system, no matter how strict the quality controls and tooling, there's a chance that human error will introduce a bug. Let's face it, bugs are a reality of software development. So, if bugs are inevitable, the question is, how do we reduce their impact? My name is Paul. I'm an engineering manager at Checkr. I live in Denver with my wife, Erin, and my three kids, Bennett, Delphine, and Hugo. What is Checkr? Checkr is a people trust platform delivering background checks to make hiring safer, more efficient, and inclusive. Background checks are often a crucial final step in the hiring process for our customers. In 2017, on October 6th, we had an 18-hour API outage where customers were unable to create reports using our API. Checkr has grown to over 150 engineers as of 2020, but in 2017, the team consisted of 30 engineers spread across approximately 6 teams. Request volume had grown significantly over just a few years, and much of the team's focus at the time was on stabilizing the system to handle the increased load. The team had doubled in the previous year, and much of the knowledge of the system was held informally by members of the team. So you may be wondering, what is a report? What does it matter if customers were unable to create a report? In the Checkr system, a report is the model that describes a Checkr background check. And customers would submit a request to create a background check using our REST API. When a customer does so, they initiate a mechanism to create a background check for a given candidate in our system. Screenings like a motor vehicle report or a criminal check are associated with that report, and all screenings and other orchestration occurs as a result of that first request from the customer. The incident began at 4:30 p.m. on a Friday afternoon. A script was run to migrate some old screening records from an integer foreign key to use a UUID instead. Within an hour, an on-call engineer on an unrelated team was paged because of a spike of errors on one of our front-end applications. The application submitted a small percentage of our total volume of reports, did not use the main API that our customers was using. Upon initial investigation, the team decided that the error was likely the result of user error. They snoozed the page. Early on Saturday morning, the same error triggered another page. The on-call engineer began investigating the error and eventually noticed a strange status code being returned by a reports create endpoint. Both our public and private report endpoints were returning 404s for many but not all of the requests that were submitted. At this point, around 9:30 a.m. on Saturday, it was finally clear that there was a major problem that impacted our APIs and not just that client application that was surfacing the error. The initial responder escalated the issue to get all on-call engineers involved. With a smaller engineering team at the time, escalation often occurred via Slack, and we used a channel called Engfire to alert the rest of the team that was on call. The rest of the team started to log in to our VPN. I remember pulling my laptop out in the parking lot of Crissy Field in San Francisco. Unfortunately, at the same time, as there was a surge in our VPN traffic, the VPN went down. We all needed to go into the office to access the internet and see production logs on our servers as a result. Finally, we made it into the office around 10 a.m. Now, with full access to production logs and all the requests that were made, we were able to resolve or identify the issue in about an hour. And shortly thereafter, we reproduced the issue. Within about 15 minutes, we had a temporary fix to solve the immediate issue. So, what went wrong? At Checkr, we strive to have a blameless culture where we learn from our mistakes and make improvements as a result of outages. An important part of that process for us is creating a postmortem document. Here's a screenshot of the template that the team uses today. The postmortem document and process has evolved over time as the team has grown, but the goal remains the same: to learn from the incident so that the same mistake does not happen again. The postmortem document captures the root cause, timeline, and follow-up action items. Identifying the root cause is an important component of the postmortem, but we value the action items as equally important. Here's what we learned. Problem 1. The root cause was exposed due to a backfill run at the start of the incident. The associated records and database level constraints were not enforced. This was in part due to the use of 2 different databases for storing reports and screenings. The root cause of the error turned out to be a combination of common bugs in programming. The backfill corrupted records in our database, and our relations assumed that foreign keys would always be present. Some screenings ended up with a nullified reference to their parent report and had a null value for report ID. When a new report was validated by active record validations, the report ensures that its associated screenings are also valid given the configuration of the report and the information provided about the candidate. A screening object is found in the database or built in memory. Since the report ID of the new report was null, the nullified screenings due to the backfill were found instead of creating a new object in memory. When the validation was called on the screening's foreign key was used to look up the report. In this case, the report could not be found, and an active record not found exception was raised. Our API routes handle active record not found automatically and return a 404 response, which is why we're seeing so many 404 responses. The backfill only impacted 2 of our screening tables. As a result of that, some types of reports continued to create successfully while others didn't. This turned out to be a contributing factor in our overall incident response because some reports were still completing. Problem 2. The second problem we identified was the 14-hour lag time we had in identifying that report creation was severely impacted. Let's go back to the incident timeline for a moment. This timeline can be broken into 2 buckets: the time to resolution and the time to response. In this incident, the time to response severely impacted the overall duration of the degraded report API. 75% of the incident's duration occurred before an active response was initiated. every hour of additional downtime was a multiplier in terms of impacted API requests. We asked ourselves what would have alerted us to the issue sooner. Remember, we did see an alert within an hour of the start of the incident, but the alert was far removed from the impacted component of the application. It was an entirely different repo. The alert pointed to a front-end service, and the service utilized an internal API that received only a small percentage of our overall report traffic. And the alert from Sentry was better than nothing, but it didn't contain clear, actionable information that a responder could use to quickly make an informed decision and assessment of the problem. Here's the most painful part of the incident from a response perspective. We actually had a monitor specifically set up for the express purpose of detecting an outage in report creation. We captured a stats-D event every time a new report was created in the system. This was exactly what we needed. The problem was that our alerting rules were far too simplistic to detect more subtle failures like we saw. When the monitor was set up, we made the assumption that we'd see close to 100% of reports failing to create. As a result, we set a constant threshold floor of about 100 reports created in 30 minutes. If the rate dropped below that threshold, an alarm would sound. Unfortunately, the outage did not impact all reports. As I mentioned earlier, only certain report configurations were impacted. As a result, we saw the report creation metric drop abnormally low, but never dip below the floor value in our monitor. The monitor was not, in summary, was not sensitive enough to detect the issue. Coming out of the incident, we identified that we needed to improve our overall observability into our systems. By definition, observability is a measure of how well internal states of a system can be inferred from knowledge of its external outputs. In this next section, I will explore tools for improving overall observability of your application, how these tools work together, and how to use those tools to craft meaningful alerts when something is wrong. There are three basic components to building an observability stack. First, you need mechanisms for gathering metrics, measurable events that indicate something about the state of your application. Second, you need to define monitoring rules that define when a particular metric is green or red. Third, your monitoring rules should be connected to an incident management platform that governs rules around on-call responders and escalation. Do not use email or Slack as your primary notification method. Let's talk a little bit about metric collection. There are three broad categories of metric collection common in web applications. There are many stacks and solutions that can address one or more of these categories. One of the most common types of metric collection are exception trackers. These are services that provide libraries to capture events when exceptions occur in your application. Examples include Sentry, Rollbar, and Airbreak. Another common type of metric collection is application performance monitoring, or APM. APM gives you access to industry standard metrics across common protocols and stacks. The benefit of APM is that you get a wealth of generic metrics basically for free. You can easily drill down to see request volume, latency, or investigate a full trace from the application to the database and back. The final category is real-time custom application metric collection. These are metrics implemented by the engineer to describe specific business processes performed by your application. These metrics are the hardest to define and maintain, but give you direct visibility into the state of your application. To visualize the kind of visibility that each of these metrics gives to you, let's imagine that your application is a black box. Exception tracking will give you targeted insights into hotspots in your application. It will give you a sense of the impact of the error through the number of events collected, where the exception is being triggered via the stack trace, and depending on the size of the application and the amount of context that an engineer has, it may or may not be clear what the overall impact of that particular exception is. As we saw earlier in the incident, exception events eventually triggered a response to the incident, but it wasn't immediately clear what, if anything, was wrong in that particular case. I like to think of APM as a heat map overlaid over your application. It's possible to zoom in on a specific part of the application, but it also gives you a high-level view of the overall health of your application. It's very useful for identifying system-wide outliers that might indicate a problem. APM often comes in handy when you haven't anticipated a specific mode of failure. A recent example of that occurred for us back in February. A configuration change was made that impacted the ability of several services in our system from authenticating with each other. As we saw some more targeted metrics begin to trend in the wrong direction, the spike in 401s that we saw in APM made it clear that something was wrong, specifically with authentication. Custom metrics give you, the engineer, a way of describing the health of specific features or components in your application. You can view each of these components as a distinct unit using the telemetry generated by the metric. Once you have the metrics, you can identify when intervention is needed. So what marks a good monitor? First, it needs to be a high fidelity indicator of system health. You don't want to miss true positives that indicate a problem, but you also don't want an overly sensitive monitor that constantly alerts on false positives. False positives tend to degrade confidence in the response, and overall, there's a risk that you won't respond when there is a true positive. Secondly, in most cases, it's best to define monitors that measure the health of a discrete feature or component. A more narrowly defined monitor will give the responder actionable information that will make a response quicker and more effective. Finally, ideally, the indicator should be a leading indicator rather than a lagging one. For example, at Checkr, we also measure report completion to ensure that reports are successfully completed. This metric would not be a good indicator of the health of report creation, however, because reports can take several hours to days to complete. Let's talk about a few types of monitor patterns that could have helped us be alerted much sooner during our incident. Recall that our monitor failed due to lack of sensitivity. First, let's talk about composite monitors. The concept is pretty straightforward. Tie multiple metrics together as a combined signal. We ultimately added a composite monitor as part of our follow-up action items as a response to this incident. We combined measurements that looked at both report and individual screening creation to spot issues where a specific screening was causing report failures. In retrospect, there are a few other patterns that could also have been used to make Monitor more sensitive to failures. One way is to make our measurements relative rather than using absolute metrics. Measuring the report created count against the total number of report creation attempts gives you a metric that easily adapts to spikes and dips in overall request volume. The second option is to use a product like Datadog's Anomaly detection monitor. Anomaly detection gives you the ability to detect anomalies in your metric. This method allows you to apply statistical methods like standard deviation to account for variability and define a constantly refitted bounds rather than defining rules against absolute values. This type of monitor has the benefit of adjusting over time as your metric patterns change, accounting for things like seasonality and long-term trends. In practice, however, so far at least, we haven't found these monitors to be super effective for our use case. They tend to be a little bit oversensitive, even when we've tried to make their bounding more flexible. So how do you build observability into your culture? Start small when building observability. Don't try to measure everything. Let's talk a little bit about how these metrics could work together in a growing business. Let's pretend that we've started our own e-commerce store to support a brand new subscription box business. When you're first starting out, your traffic is very low and you have a small team that understands the full system. It's likely that when an exception occurs, you will know pretty quickly what and why an error has occurred. Traffic is inconsistent at this point, so it's hard to predict how many boxes will be purchased and how many shoppers are even interacting with your store. As your store starts to grow, it becomes harder to understand how everything works together. Maybe you've added new features to your product page and recently added coupon codes as a feature in your checkout process. How do you know that your core store features are still working? That's where custom metrics start to shine. You can start to instrument higher volume events like add to cart first. And as traffic continues to grow, you can add on other critical features as discrete monitored events as well later on. When it comes to implementing custom metrics, ask yourselves two questions. What would I want to know before my customer notices? Target monitoring in places where you're delivering the most value to your customers. And secondly, what systems are most brittle and at risk of breaking? As your system expands in scope, introduce more structure. Consider defining the importance of specific services or components more explicitly and mapping those requirements specifically to those tiers of importance. You can map specific requirements like monitoring and on-call to those tiers so that it's very clear what types of reliability and observability need to be in place given the importance of that system, and then constantly reevaluate the importance of those particular systems. To recap, bugs are inevitable and are a fixture of software development. But our responsibility is not over when we press deploy. Observability is the foundation of building a reliable system. Start small, turn key tools like exception trackers and APM. Turnkey tools like exception trackers and APM provide a huge amount of value with limited investment. Measure things that are critical to your application. Don't try to measure everything. And finally, iterate on your monitoring rules. Tune them to make alerts of higher fidelity and more actionable for your responders. Thank you.